In this part, we will focus on the experimental part of TERS and on practical issues. For a TERS experiment, we need a scanning probe microscope, and the most used one are the scanning tunnel microscope, the atomic force microscope, and the shear force microscope. Then we need, of course, an efficient TERS tip. We need also a spectrometer and an optical coupling system allowing the excitation of the tip LSPR and the collection of the TERS signal. In this case, is a side mode configuration, and this specific equipment is commercialized by Horiba Scientific Company. So, as we already have discussed, a scanning probe microscope relies on the local interaction of a tip that for TERS has to be plasmonic tip and the sample. So scanning the tip over the surface, we can reconstruct the topography of the sample. One of the most used scanning probe microscopes is the STM, where the local interaction is the tunneling current flowing between the tip and the sample, when a bias voltage is applied between them. STM allows very small gaps lower than 1 nanometers, so it is a desirable configuration for a gap mode, for example, and to create pico cavities for atomic resolutions. However, the strong limitation of this configuration is that STM is limited only to conductive samples. Another SPM frequently used is the atomic force microscope, AFM, where the interaction between the tip and the sample is due to the atomic forces, the van der Waals forces, so that are monitored registering the deflection of an elastic cantilever observed with the reflection of an IR laser on top of the surface of this cantilever. IFM is very appealing in TERS because it allows TERS analysis also on non-conductive samples, but it is usually less efficient compared with the STM TERS because of the different plasmonic properties of the tip in the two cases that we will consider later. AFM has different operating modes. One of the most versatile is the so-called tapping mode, where the tip touches the sample in an intermittent way. So it oscillates between the contact region and the non-contact region in this sketch of the interatomic potential. However, as you can see here, the oscillation of the cantilever are usually in the range of 20-60 nanometer. That are huge distances if we consider that the near field region is confined in about 10-15 nanometers. So that's because in IFM, TERS is used the contact mode, where the tip touches the sample in a constant way. However, in order to optimize the scan time of the surface and also avoiding the possible tip damages, there are some combined modes that allow the scan of the surface in a tapping mode and to collect the TERS signal in a contact mode. Shear force microscopy rely on the contrary on the oscillation frequency of a quartz tuning fork. The tuning fork oscillates always at 32 kilohertz. And when the plasmonic tip is attached on one arm of the tuning fork, this frequency drops at about 27-28 kilohertz. So when the tip is in the near field region, the interaction with the sample will modify the oscillation of the tuning fork, allowing the reconstruction of the surface topography. In this case, the oscillation amplitude is small, and shear force microscopy allows TERS analysis. Also on non-conductive samples with no need of optical alignment for monitoring the tip position. We are relying only to the monitoring of the oscillation frequency of the tuning fork. The tip can be mounted also in this in this configuration, not only in this configuration. So in this case, we are monitoring not the shear force, but the normal force. And another advantage of this configuration is the easy access for the optical coupling of the excitation for an excitation laser beam in TERS. You see there are a lot of free space that we can use to put our objective. Here it is summarized all the possible excitation geometries for TERS that are separated for transparent samples and non-transparent samples. For transparent samples, we can use on-axis excitation with a radially polarized beam. And with this configuration, we can benefit of high numerical aperture objectives, and so we can collect we can have an efficient signal collection. On the other side, for opaque samples, we can use the side mode configuration or the top illumination. In this case, we need objective with lower numerical aperture and linearly polarized beam with at least one component, one electric field component parallel to the tip axis. However, we can benefit of an easy in this configuration. We can benefit of an easy access for optical coupling between the laser and the tip. Finally, we also have another configuration employing a parabolic mirror. In this case, we need a radially polarized beam that converge on the focus of the parabolic mirror, where we can locate the our plasmonic tip apex. This mode has an high numerical aperture and therefore also an high signal collection efficiency, and can work also with non-transparent samples. However, the optical alignment of this configuration is quite delicate. Let's now consider the TERS probes features. We can have different tips according to the scanning probe microscope that we want to use. The most simple probe that we can think about for TERS is represented by a single plasmonic nanoparticle placed on top of the tip apex. However, placing with high precision a plasmonic nanoparticle on top of the tip apex can be difficult and time-consuming. A faster approach to have a nanoparticle on top of the tip apex is to use to placing in a random way many nanoparticles on top of the tip on the tip shaft by evaporation or chemical methods, and by chance one of these nanoparticles will be at the end of this tip apex. Another TERS probe frequently used is represented by an AFM probe. So these are conventional AFM probe, and usually there are these thin film evaporation of a plasmonic material, such as in this case gold, and we will end up with these tips that are completely coated by a metallic film. These probes are quite robust and can have a tip radius of about 30 nanometers. Finally, we have also a bulk plasmonic tip, where the tip is completely formed by a metallic bulk wire. And these are very appealing because they are very sharp and with a tip radius that is lower than 30 nanometers. From now on, we will consider in close detail also these kind of tips, which can be easily fabricated by electrochemical etching methods. So in this case, for example, I will show you a simple double-step etching method for the fabrication of bulk gold tips, starting from thin gold wires. What we need is a voltage generator a crystalline gold wire that is used as an anode, and a platinum ring that acts as a cathode. The wire and the ring are immersed inside the solution, which is composed by ethanol and hydrochloric acid, and the process, or the work process, is inspected through a stereo microscope. So when we put a bias voltage between the wire and the ring, there will start an etching process at the meniscus formed by the air solution interface at the wire to the wire position. The etching at the meniscus results much intense if compared to the etching in the bulk inside the solution. The higher is the voltage, the faster will be the process. But the faster is the process, the more defects are present on the TERS probe. The idea here is to optimize the etching time and keeping good feature of the TERS probe using in a first stage an high voltage, and then decreasing it in a second stage. So here you can see a video of the etching process. We are starting with a bias voltage of 5 volts, and you can see that there is a strong bubble production here, which can move the wire inside the solution. But when we reduce the voltage at about 2.2 volt, there is no more bubbling, and the process is more stable. At the end, the process will self-terminate when the piece inside the solution will drop. So now there is here the meniscus, and the gold is consuming in the bulk. Okay, now it should drop. So now it is very thin, and the piece inside the solution is too thick, and it will drop. Now the process self-terminates. So here we can see the different stages of the tip formation seen at the electron microscope. So at the end of the process, we end up with this kind of tip having this particular shape and a very small tip radius, generally lower than 50 nanometers. But in some cases, we can also have TERS tip with the radius of only 12 nanometers. And together with a small apical angle, in this case 24 degree, we have ideal TERS tips, since the small radius ensure high field enhancement and high spatial resolution, while the low apical angle ensure a broad LSPR covering the whole visible spectrum and permitting a large tunability for the excitation laser beam. So let's now see how to couple the laser beam and the tip in an STM configuration. In this specific equipment, we can use this probe holder that is placed in this position here inside the STM microscope. The connection with the sample is done through this sample holder, having this spring contact that we put on top of the surface. And we can inspect the probe position through both these two objectives, from the top and from the side. First of all, we need to do a coarse alignment in order to see the tip from both the cameras. From the top, this is the shape of the wire of the tip, and from the side. So when we are in this condition, we can start with the semi-automatic approach using a piezoelectric scanner. on top of which is mounted the side objective. So we can do both an XY objective, so in the X and Y direction. We can do a map looking for the reflected fluorescence. So we are monitoring the intensity of the fluorescence scattered by the tip, and reconstructing the tip shape, and we can locate the tip apex in correspondence to the maximum fluorescence intensity. So when we put we can put the laser position exactly in this point where there is where we think that there is our tip apex. At this point, we can do another scan in the orthogonal direction, this times in the X and Z direction, trying to maximize the intensity also in this case. We will have this kind of elliptical shape where the maximum focus is in this position. At the end of the alignment process, from the side camera, you should have a situation like this when the laser is on with this round spot at the very end of the tip. While when there is no laser, there is this situation. So let's now think to the sample. We have seen that the best results are obtained in a gap mode configuration. Usually, the metal used as a substrate are these kind of commercial crystalline film or of gold or silver. In this case, we have gold. A common procedure to optimize the quality of the crystalline film is represented by the flame annealing process. It consists in putting the gold film surface in close contact with the flame and for a few seconds, and when it starts to glowing, you retract from the flame. This is repeated a couple of times, and this permit to have flat gold terraces which are more extended than without doing this process. And this is a typical STM image of this kind of samples. You can use now you can use this kind of flat gold surface to create self-assembly layer of azobenzene, for example, or thin films of dye molecule, just immerging the gold substrate inside the solution for a few hours. So at this point, we have our sample we put inside the microscope. We already have done the laser tip alignment. So we need to bring in a working distance the sample and the tip. To do this, we first choose our feedback interaction. That in this case we choose the tunneling current, so the current. Then we need to set both the bias voltage between that we want to apply between the tip and the substrate, and the current value that we want to flow between the tip and the sample during the scan, the set point value. Typical values for the bias voltage are range from 1 volt to fractional volts, like 0.1 volt. While for the tunneling current, we have typical current of 1 nanoampere, or even less, like 500 picoamps or 100 picoamps. So now we can start to carefully approach the sample and the tip, monitoring the tunneling current. When the tip is in contact, you can see that the current value that we can see on an oscilloscope, it is the one that we have set in our set point. This is an optical image of the tip at few microns of the surface. You can see starting to see this reflection. And this is when it is in contact, when the feedback is on. So it is flowing exactly the current value that we have set. This is a very delicate point that need a lot of attention if you don't want to end up with tips like this. So at this point, we can shine the laser on the tip and form our TERS experiment. So this is with the signal with the tip in contact, and this is the signal with the tip far from the substrate.